Hello, everyone. Have you ever wondered how to make sense of the overwhelming amount of information we encounter on a daily basis? Right from news articles to research papers to novels. Like the need to quickly extract key insights has never been so critical. And in today's presentation, I'm excited to present to you TextSum, an AI-powered solution designed to transform the way we process information. So today's agenda for the presentation is the introduction, the goals of the project, a brief overview of the data pre-processing pipeline, most importantly, the model architecture, the results obtained, the challenges faced while making the project, the conclusions derived, and last but not the least, the future work. So what exactly is text summarization? Text summarization basically helps us condense lengthy content into concise versions, thus saving time while retaining key information. It comes in two forms: extractive, which selects key phrases from the text, and abstractive, which generates new sentence based relevant to the main ideas. And in today's fast paced world, it is crucial to manage information overload and gain insights efficiently. In order to do that, applications range from summarizing legal documents to creating research abstracts and news summaries. Now, this project particularly focuses on automating textual summarization using deep learning techniques. And in order to achieve this, I'm leveraging the power of Bi-LSTM model, which which is used for handling sequential data like text, and introducing a new local attention mechanism. And finally, I'm emphasizing on improving the computation efficiency by optimizing our approach to ensure the system. I ensure that the system is not just effective but also practical for real world cases. I'm going to give you a brief overview of the data that I'm using in this project. So I'm using a CNN Daily Mail news dataset, which I downloaded from Kaggle datasets. This contains news articles and corresponding human written summaries in the English language. It has three fields: ID, article, and highlights, and these are the number of records in each of the datasets. Here is a snapshot of the dataset, the raw snapshot of the dataset which I used, the raw dataset. And this is an example raw text and an example raw summary. Now that we know the dataset we're going to use, let's explore the trends in data using data exploration. So this is coming to the first type of analysis, which is text and summary length analysis. Um, it compares the lengths of the input texts and their corresponding summaries. And as we can see, the maximum text length is beyond 2000 and the maximum summary length is beyond 1000 words, which showcases the variability in data. But for a clearer picture, I calculated the 90th percentile for both the text length and the summary length, which was calculated to be around 712 and 48 words. Those histograms, they visually show that most of the texts are much longer than the summaries, and which reinforce the need for effective summarization to condense this information. Not only that, I also did the word coverage analysis, which evaluates how well the summaries represent the original text. Here, the average summary coverage is 76.3%, which means the summaries capture a significant portion of the key information. This high coverage suggests that the task leans towards extractive summarization task because, as I mentioned earlier, the summaries directly reuse the words or phrases from the source. Now coming to the data pre-processing pipeline, I'll just brief you about it. It takes place in 5 steps. In my project, I combined step 2 and 3, but technically it takes place in five steps. The first step being data cleaning, which replaces contractions such as shouldn't, couldn't, don't are converted to should not, could not, and do not to remove the punctuation marks. And we also remove the stop words such as I, me, pronouns and stuff, which do not contribute a lot to the semantics of the sentence. And we also lowercase, we convert the sequences to lowercase. Then we come to step 2, which is tokenization. We split the text into individual words, and then those individual words are converted into meaningful numbers using vectorization. Steps 4 and 5, I'm going to discuss in the next slides. Coming to step 4, which are token embeddings. These go deeper by extracting semantic information from the vectorized text which are previously tokenized. And those embeddings help the model understand the word meanings and the relationships. But in addition to token embeddings, I've also made use of positional embeddings. And in this project, I've created a customized positional embedding layer, which are trainable, and they take the length of the sequence into consideration. So combining the semantic information and the positional information, we get the combined embeddings. Because positional embeddings help the model understand the order of words in a sentence. So it knows that the cat chased the mouse, that it means that the cat is doing the chasing and not the mouse. And this is basically the pre-processing flow, which starts from the input data, text vectorization, dataset loaders, which I'm going to come to in the upcoming slides, token embedding, positional embedding, and the output data. Coming to the most important part, which is the model architecture. Here, I implemented Bi-LSTM layers, 3 Bi-LSTM layers in the encoder and 3 LSTM layers in the decoder. I also implemented the aforementioned dynamic local attention, which leverages dynamic window allocation technique, which I'm going to discuss in the upcoming slides. Coming to the encoder part, which is the first key step in summarizing text. Its role is to process and understand the input text, and to start with, vectorized text are passed to positional embeddings, which are passed through Bi-LSTMs. Now, those Bi-LSTMs, they are designed to analyze the text both in forward and backward directions, so it captures context from all directions. And additionally, in order to ensure stability and better learning, I've introduced batch normalization layers over here, as you can see, which balance the inputs for consistent training and gets them in between the values 0 and 1. Finally, we can see that Bi-LSTM layers uh, output 2 types of states: cell state and hidden state, two of each. Since Bi-LSTM is bidirectional, there'll be 2 cell states and 2 hidden states. Those states are concatenated in 2 layers. One is state, both the hidden states are concatenated in one, and both the cell states are concatenated in the another one. This setup ensures that the model grasps the most important information from the text efficiently. Coming to the decoder part, this takes the process information from the encoder and generates the summarized text. It starts with binary inputs, like the summaries are created into binary inputs representing summaries, and we use the concatenated hidden and cell states from the encoder to set the initial context. In order to avoid overfitting, I also included dropout sequences in each of the LSTMs, which help the model generalize better. Then we come to the attention outputs, which is which are calculated using the dynamic attention layer, which I'm going to discuss about in the upcoming slides, which are then transferred to the batch normalization layer for ensuring accuracy, and the output is refined through a dense layer, a time distributed dense layer, to produce the final summarized out text. This is the most exciting part which I've been working on, which is the dynamic attention mechanism. Let's say this is the input text, and let's say we set a fixed window size for local attention. Local attention, what it does is it it has a window, and it focuses on a particular part of the text, and to what part to focus on and to what part to give attention to. But in dynamic attention mechanism, we can change the size of the window. Actually, we don't have to do it. We can let the model decide, and it can be changed dynamically on the basis of the length of the sequence. And this is a brief diagram of the dynamic attention mechanism, where the decoder outputs are passed into the dense layer. The dynamic ratios are calculated through the dense layer, And using the actual sequence lengths, they are multiplied with the dynamic ratios to set the window size. I also set a hard cap on the window size to decrease the computation load and increase the efficiency of the model. The system requirements, I use a 16 GB RAM. I use 16 GB RAM of CPU, and I use two GPUs, 16 GB NVIDIA T4 GPUs. I set the mix precision to mix float 16, which I'll discuss later. And I also implemented mirror strategy to utilize both GPUs judiciously. Coming to the results section, I achieved an accuracy of 95.22% on the training dataset, and I achieved a validation accuracy of 94.86. And the close match between the training and validation accuracy suggests minimal overfitting, and this highlights the robustness of the pre-processing pipeline and the attention mechanism. I also achieved a testing accuracy of 93.8 upon the evaluation of the model. I use an F1 metric score because it is important for evaluating text summarization where both relevance and correctness matters. So here I achieved a high F1 score of 0.9674, which indicates the model's ability to generate summaries that align well with the ground truth data. And additionally, I also used BLU scores for different n-grams. For unigram, I got this for bigram and for trigram. I'll explain how exactly this works in brief. So for n grams, what it does is that it considers n number of words at a single time for a particular context. In case of unigram, it only considers individual word matches between the ground truth and the predicted labels, and it basically calculates the similarity between the two, which is the basic gist of the BLU scores. And here I used unigram, bigram, and trigram. Usually, BLU scores in those scores, as the n-gram increases, the BLU scores decrease. But in our case, it's the opposite, because as we can see, the trigram has the highest values, which suggests that better contextual understanding is done by the model. Additionally, I also calculated the confusion matrix, and this is sort of how I calculated. This is a single sample, the true labels which are converted to binary, and these are the predicted labels which are converted to binary. And we match each of those values to produce the confusion matrix. There are certain challenges which I faced while creating the project, which basically I dealt with managing large data sets along with computational and memory management. And it often required implementing efficient data loaders, as I mentioned earlier, and use batch processing. So over here, I used TF.data API to streamline the dataset management and improve pipeline performance. Also, I was challenged with inconsistent tensor shapes, and it resulted in consequent debugging in the custom layers. I also incorporated novelty in the project without overcomplicating the model structure, um, because ensuring proper broadcasting and tensor operations was challenging due to dynamic computations like attention scores. So extensive testing and visualization of intermediate outputs was crucial for debugging this layer. Also, I faced limited computational resources for model training. So I evaluated multiple approaches before finalizing a design, such as number of layers in Bi-LSTM, number of layers in LSTM, to improve the performance without unnecessary complexity and increased computational load. I also faced long training times, which I dealt with, which I tried to deal with. I tried to reduce the training time by optimizing the pipeline with mixed precision, which basically dynamically sets the data types differently for algebraic operations like matrix multiplications and gradient calculations, which usually require 32 data types. Last but not the least, The model was prone to exploding or vanishing gradients, which might lead to numerical instability in cases of accuracy or losses. And I addressed this issue by using gradient clipping and initializing weights using proven methods such as uniform distributions to stabilize training. The conclusion of this project is um, I basically demonstrated the potential of leveraging Bi-LSTM with a dynamic local attention mechanism, and I also successfully developed a novel attention mechanism as well as mentioned earlier. I achieved high performance on multiple evaluation metrics, including F1 score, accuracy, and BLU score. And I also demonstrated the scalability and robustness of the model through introduction of custom layers, through efficient handling of large data sets, and also introduced a reproducible and modular pipeline for future adaptations and experiments. Coming to the future work, I would like to extend this project to advanced real world cases such as legal document analysis, academic research summarization, and more. I would also like to explore transformer-based architecture such as BERT or GPT for further performance improvements because they represent the current gold standard of models in NLP. One more thing I would like to do in the future is expand to multilingual data sets to enable global applicability so that because adapting the model to various languages would require addressing challenges such as tokenizing for different scripts and different grammar rules. Last but not the least, I would like to optimize this model for deployment on edge devices or low resource environments such as mobile apps. Uh, and these optimizations will basically ensure that the model is lightweight without compromising on the performance. Thank you and happy text summarization.